Hi everyone, I'm Janani and I'm here to talk about online vector scheduling in the fully dynamic setting. This is joint work with Ravishankar Krishnaswamy, Varun Gupta, and Sandeep. Let me begin by defining the problem. We have m identical machines, and at each time step, we're given a job to be inserted or deleted to some machine among these m machines. Each job has d dimensions, and we're given a positive real number as the load in each dimension as the input. There are n total insertions or deletions. We don't know what n is because this is the online setting, and at each time step, we're given a job. Our goal is to minimize the make span, which is the maximum load over all machines and all dimensions in our assignment. Let's look at an example. Let's say we have only two machines and two dimensions. We're given a job 1, 4 as input. This means the job has load 1 in the first dimension and 4 in the second dimension. And let's say we insert it into the first machine. Now we want to insert job 2, 1 and we send it to the second machine. If we want to insert job 3, 1, it doesn't matter which machine we send it to because the make span is going to be 5 either way, and we're going to send it to the second machine. Finally, let's say we're given job 7, 7, and this job will be inserted to the first machine because this has a lesser make span. We have a make span of 11 with our assignment, but it's not hard to see that a better assignment exists where this heavy job is present on one machine and the other jobs are present on the second machine. And this make span is 7. Let's see what's going to happen with deletions when we start with this assignment, which was good for us. If we want to delete this heavy job 7, 7, we're going to end up with an empty machine. So this suggests that we need some form of reassignment of jobs between machines, and this is going to be called recourse. This gives us our secondary goal. We want to minimize the make span of our assignment at every time step while ensuring that we do not use too much recourse. Let's look at some previous results here. In the insertion only oblivious setting, there is a randomized algorithm which gives a competitive ratio of log d over log d and no recourse. In the oblivious setting, we just mean that the adversary does not have access to the randomness used by the algorithm. In the insertion only adaptive setting, where the adversary can look at the randomness used by the algorithm, there is an algorithm which has a competitive ratio of log d over log d, same as the insertion only oblivious setting, and again no recourse. For these two settings, this log d over log d ratio is tighter. Next, we have our result. In the fully dynamic oblivious setting, we have an algorithm which has a competitive ratio of log d over log d and constant recourse. This means that any job is reassigned a constant number of times throughout its existence. In the fully dynamic adaptive setting, we give an algorithm which has a competitive ratio of log d and a recourse of d times log n times some factor gamma, which is the factor by which the optimal make span changes during this job's existence. Before we proceed to the algorithm, let's look at two lower bounds on the optimal make span. The first one is that the optimal make span should be at least as high as the average load in any dimension. This is because in the optimal assignment, there should be at least one machine for every dimension k where the load exceeds the average load. And we can also say that the optimal make span should be higher than the maximum load over all dimensions and all jobs. Again, this is because in the optimal assignment, there should be at least one machine for which this job is assigned And on this machine, the load is going to be higher than this value. So with these two lower bounds, the average load lower bound and the maximum load lower bound, let's start by designing some algorithms for the insertion only setting. First, we know that there is a deterministic greedy algorithm in the single dimension case with a constant competitive ratio and a constant recourse by Westbrook in 1994. We can't use this algorithm directly because the number of dimensions for us is d. Instead, we're going to do something called flattened greedy. So let's say there are these M machines and they already contain some jobs assigned to them. We're given some job J, which is to be assigned to one of these machines. We're going to flatten the load in the d dimensions of this job J into one dimension by taking the sum of these loads. Then we're going to pick a machine which gives the least makespan based on this sum. The competitive ratio here is going to be D, and we're not going to prove this. It's not too hard. This competitive ratio is not good for us, so let's try inserting jobs randomly. Again, we have these M machines, and there are already some jobs assigned to these M machines. When we want to assign job J, we're going to just pick a random machine M of J and assign job J to this machine. In expectation, the load on each machine is going to be ALK of J in dimension K. But the competitive ratio becomes log of M times D because the makespan may be high, and this is from Chernoff bound. We're not going to prove this either. In our next attempt, we're going to combine both the random algorithm and the greedy algorithm this way. We're going to assume there are two copies of these machines called random and greedy. So there are M machines in random and M machines in greedy. Both these copies may already have some jobs assigned to them. We're going to set a threshold of some order of lambda times ALK plus maximum load, where this lambda is the competitive ratio that we want, which is log D over log log D. So when a job J is to be inserted, we're going to pick a random machine M of J and just check whether on addition of job J to machine M of J, is the threshold exceeded or not in every dimension. This threshold is set only for the random machines. So if this threshold is not exceeded on addition of job J in any dimension, then this job is going to be added to the random set of machines. If, when we're trying to insert some job J prime, this threshold is exceeded in some dimension K, so let's say job J prime was assigned to machine 1 randomly, and this threshold is exceeded, then this job J prime is going to be added to the greedy set. So how we handle this greedy set is the same as the flattened greedy algorithm that we saw earlier. We said that the competitive ratio of this algorithm is going to be theta of D, but when we assign jobs this way, only 1 over D fraction of all the jobs is sent to the greedy set. And this gives a low competitive ratio. We're not going to prove this fact now, we'll prove it later. A brief sketch of this analysis of this random plus greedy algorithm is here. So for the random machines, we don't exceed the threshold because we never add any jobs which go beyond this threshold. And each job is going to be sent independently to the greedy set with probability at most D, and this is from the choice of our threshold and Chernoff bound. In the greedy machines, even though the competitive ratio is theta of D, since only 1 by D fraction is sent to them, the competitive ratio remains a constant. Now, how do we change this algorithm when jobs can be deleted as well? In the insertion only stream, we know that the optimal makespan always increases because jobs are only added. But with deletions, the optimal makespan, the average load, and the maximum load are dynamic quantities and can increase or decrease while we run the algorithm. To avoid this, we're going to use something called the prefix property. We're going to set the thresholds only based on all the previous jobs which have been inserted before job J. So the threshold for job J is going to be the same comparative ratio lambda times the average load in dimension K till job J and the maximum load over all dimensions till job J. Any job inserted after J does not affect this threshold for job J. Because of this, our quantities ALK of J and ML of J can only decrease. Now, when we want to insert job J, we again have two copies of these machines, random and greedy, and they already have some jobs assigned to them. We're going to set the threshold for job J as, again, order of lambda times ALK of J plus ML of J. So this threshold is compared to the actual load on machine M of J in dimension K in the random set alone. M of J is the random machine picked for job J when we insert it. If this threshold is not exceeded when we add job J to the random set in any dimension K in machine M of J, then we're going to leave it in the random set. We just want to know that this random choice for job J is going to be fixed when it is inserted for the first time. We never change this random assignment as long as job J exists. If this threshold is exceeded in some dimension K, then job J is added to this greedy set. Now, when we want to delete jobs, if job J is present in the greedy set, we can just normally delete it and perform the one dimension updates from Westbook 94 to balance the load. If job J is present in the random set, deleting it may cause some issues for us. What may happen is, for some job which was inserted after J, the threshold may decrease. Because of this, we perform a stabilization procedure as follows. If we change the thresholds and reinsert jobs every time a job which was inserted before us is deleted, then this recourse becomes high. So instead, we're only going to update these thresholds if they drop below half of the original factor to change this job's assignment. So when this threshold drops by a multiplicative half factor, we're going to update the threshold and reinsert this job as if it was inserted for the first time. This is going to give us a low recourse and a low probability of going to the greedy set. Let's see this in a bit more detail. When we want to delete job J and it is present in the random set, we said that threshold may decrease for jobs inserted after J. So for some job J prime inserted after J, we're going to check if this threshold reduces to threshold K of J prime by 2 for any dimension. And if this does not happen, we're not going to do anything. We will just remove job J and proceed to the next time step. Otherwise, if this threshold does decrease, then we're going to recalculate this threshold in every dimension for this job J prime and reinsert it in the random set or greedy set appropriately. If this job J prime was reinserted into the random set of machines, it is not going to change its assignment because it will be reinserted into the same machine it was assigned to begin with. But if it was sent to greedy, it may change its assignment and it may be moved to the greedy set. This is our entire algorithm. And now let's look at what happens to the recourse. Recourse is going to be constant because a job is reassigned only when it is shifted from random to greedy, and this happens at most once in our algorithm, or it may be reassigned inside greedy while we do load balancing from the single dimension algorithm. And this is also constant from Westbook 94. So totally, the recourse is going to be constant. We want to prove this claim that any job is sent to greedy with probability at most 1 over t to prove that the competitive ratio is going to be low. When is a job sent to greedy? If it exceeds the threshold when it was inserted, then it may be sent to greedy without ever going to the random set. Otherwise, if some job before it is deleted and this threshold reduces by a half factor, it may be sent to greedy when it exceeds the threshold during this reinsertion. We will show that the probability that this job goes to greedy is at most 1 over d. Let's fix our threshold now to be some constant 12c times lambda times average load in dimension k till job j and the maximum load. Then, by Chernoff bound, we can see that the probability that this threshold is lower than the actual load is going to be at most 1 by d raised to c. But this probability has this threshold appearing in the numerator of this exponent, and we're going to use this. Just a remark that we can use Chernoff bound because our choice of the random machines were independent of each other for each of these jobs. So we have this equation. We're going to use this trick that we checked for these thresholds only when these thresholds were reducing by a half multiplicative factor. So because of this, if we start with some probability, we know that totally the probability that this job is sent to greedy by any dimension k is going to form a geometric series by union bound. This bound is over the number of times we try to reinsert job j because of other deletions. The total probability does not exceed 1 by d raised to c minus 1. So for any c greater than 2, with union bound over all dimensions, we prove the claim. Now, for the competitive ratio, in the random set, let's just look at the last job which was inserted. So in dimension k, we know that this load is going to be less than the actual load till job j was inserted, along with the maximum load before job j, and this is going to be less than twice the threshold plus the maximum load because this job j was not moved to greedy, and this is going to be less than the competitive ratio times opt directly. In the greedy set, we prove that only 1 by d fraction of all the jobs are inserted in expectation. So from Westbrook 94, we know that the total load is a constant times the sum of the average load and the maximum load, and this also is going to be only a constant times the optimal Makespan. So in conclusion, we gave a randomized algorithm that handles deletions with a log d over log d competitive ratio and a constant recourse. Let me end with a few open questions. So we said in the insertion only setting with oblivious adversaries, this log d over log d bound on the competitive ratio is tight, but it's not clear if recourse can help us beat this lower bound. And we don't have any recourse dependent lower bounds in the dynamic setting. Say if we bound the recourse by some constant, what is the best competitive ratio we can get? And it's also unclear how to extend this algorithm to adaptive adversaries and reduce the recourse, and also how to de-randomize this. This ends my talk. Thank you so much for listening.